Hello, this is the second part of section 1.2, and we are going to start with Roman numeral 2, scientific notation, and finish this out. We've got section 3 about precision and accuracy and significant figures, and section 4 about problem solving strategies, which is also known as dimensional analysis. All right, so scientific notation is defined as the standard format for expressing any number as a number between 1 and 10 multiplied by a power of 10. So the standard format is some number m times 10 to some power. For example, here is how to write the speed of light in scientific notation. So the speed of light is 299,792,458 meters per second. And that's a lot of numbers to have to write. So first of all, we've got to move the decimal so that there is only one number digit between 1 and 10. So right now, the decimal is after the 8. And we've got to move it over between the 2 and the 9 so that there's only one number digit. Now, we need to count the spaces that the digits that we just moved the decimal over. So boing, 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 boing. There's 8 decimal places that it got moved over. Now we have to pay attention to whether we move the decimal to the left or to the right. If we move the decimal 8 places to the left, then our exponent is going to be positive. But if we move the decimal point any digits to the right, then it would be negative. So that makes our final answer to be 2.99792,458 times 10 to the 8th power meter per second. All right. Now, just to keep it straight, about moving to the right or the left and whether it's positive or negative, here is a mnemonic that I came up with. And if you think of one that's better for you to be able to remember, then by all means do that, because that's the whole point, is you want something that's going to make it easy for you to remember. But this is just what I came up with. So on step 3, we said that the decimal point moved to the right. So it was negative. So if it moved to the left, it would be positive. So I'm associating the letters R and N with right and negative. So right now, if you have to move the decimal to the right, then you're going to remember it's negative with right now. And if it moves to the left, it's going to be positive. So if you remember the word please, so positive, left, right is negative. So it's a little backwards, but that's just what I came up with. All right, so here's another example. So instead of it being a really big number, this is an ultra tiny number. We're going to talk about what the mass of one electron is. So if we could weigh one electron, it would be all these zeros, 9109. So first of all, we've got to find one digit, the first digit that we come to, that is between 1 and 10. So that's going to be this 9 right here. So we've got to move our decimal over here after the first digit that's not a 0. All right. So does anybody want to count all this? Okay, we've already done it for us. So there are 28 places that we moved our decimal over, 28 places. So we moved it. Did we move it to the left or the right? We moved it to the right. So right now, that makes it right now is negative. So 9.109 times 10 to the negative 28th. Having trouble finding a place to put that where it's not in my way. Okay. Thanks. Okay. All right, our next topic is precision and accuracy in measurement. So precision is how consistent or reproducible a measurement is. Accuracy is actually how close the measurement is to its exact true value. So here are 4 bullseyes with all the different combinations. So of course we want to hit the bullseye in the very center. Now, this person was pretty close because they got 1 bullseye and 4 are touching the red or the white, the next red or white rings. So that's high accuracy, but they're a little bit spread out. So high accuracy, low precision. Now here, person number 2, they're not very accurate because they didn't get in the middle, but they were very precise because they always hit the same area of the bullseye. Now, in the third bullseye target, all of their arrows hit in the white, a little in the red, but they're all clustered really close together. So they're both accurate and precise. And then the last one, of course, is kind of all over the place. They did not get any in the middle ring, and one is just touching the second ring. The rest are scattered out, so low accuracy and low precision. All right. Now we want to talk about defined or exact numbers versus uncertain numbers. So defined or exact numbers are going to be very accurate and precise, both things. So we know that the definition of 1 meter is that it's 100 centimeters. And anytime we have 100 centimeters, it's going to be 1 meter. We know that there are 60 seconds in a minute. These are definitions. Okay. Now, exact numbers are things that we can count, and there's no partial pieces, it's all whole things. So right now there are 6 students in our chemistry class, not 5.62 or 6.09. That's not possible. If I buy bananas at Kroger, I buy 5 or 3, I have to buy a certain number. I can't buy a half or 2 pieces or whatever. Okay, now uncertain numbers. After recording a number digit that a scientific tool or machine allows, whenever possible, include 1 additional estimation digit. Now you're probably thinking, what in the world are you thinking about? Okay. So in this picture, here we've got ribbon A right here held up against a ruler. So you can see it's past 1 centimeter, and then each one of these little marks are millimeters. So it's not exactly 1 millimeter past there. It looks like a little hair past there. So that is the number that we're not certain about. So this uncertain number is 1 additional digit that we can obtain by estimating. There's not marks on whatever machine or tool that allows us to count. We just kind of have to eyeball it and estimate the best we can. Now, when I say estimate, don't go crazy and think that that's 1.12492. We can't, we're just going to estimate one number, not a whole string of numbers, one number. So this ribbon A, I would say if you wrote down 1.1 centimeters, I mean, it's somewhere, it's definitely obviously between 1.1 centimeters and 1.2 centimeters, either there, but neither one of those are as accurate as what we could be. So if we were to guess, estimate 1.11 centimeter, or that's a little bit better of a guess. So because there aren't any smaller markings on the ruler, we can't say that we're measuring that. That's the digit that has the level of uncertainty to it. So it's the best that we can do. What would you say the length of ribbon B is? So it's definitely, so here's 9 millimeters. So it's definitely between 1.9 centimeters and 2.0. I would say somewhere but either 1.95 centimeters or 1.96 centimeters. Okay, but the 5 and the 6, that last digit right there is our uncertain number that we're guessing about. All right. So now we need to talk about significant figures. Now, for short, people call them sig figs. So in science, measurements are generally recorded to the first uncertain digit. Now, that digit that we just talked about, that we guessed about, that's the uncertain digit. In any scientific measurement, all certain digits, along with one uncertain digit, are known as significant figures or sig figs. Using sig figs allows scientists or engineers to distinguish between certain and uncertain digits. So here are the main guidelines to determine how many sig figs a number has. Now, your book numbered these, and I think it's easier to learn them in a little bit different number. So I kept the number that they said, but I've reordered them. So that's why it's 14352. So number one's the easiest rule. All non-zero digits are significant. So if you see a 1, 2, 3, 4, 5, 6, 7, 8, or 9, it's a significant digit. Number 4, all zeros that you find in between any non-zero digits are significant digits as well. So I colored them orange. So in 1009, the 2 zeros in the middle, or 4.00052, those zeros are all significant digits. Rule number 3 says that all zeros at the end of a number that has a decimal point are significant. So 10.000, that means somebody measured that out or looked at a ruler, they didn't just write a bunch of zeros on there. Not in science anyway. And then 0.7900 or 50 with a decimal right after it. If somebody put a decimal after the 50, then that zero counts. If they do not have the decimal there and they just say 50 people are on the bus, I don't really think that they went and counted every single person. I think they're just kind of eyeballing and thinking that looks like about 50 people. So if there's a decimal point after the zero, then you count it as a significant figure. Rule number 5, zeros at the end of a number that do not have a decimal point are not considered to be significant. So 30, 100, or 5 million, all those zeros, most of the time people estimate when they have those big numbers like that. And then number 2 To count the number of sig figs, we start at the left and work our way to the right and we find the very first non-zero digit and then keep counting until the first uncertain digit. So usually the digit that's on the farthest right, unless it's a zero without a decimal point, like for rule number 5. So let's practice on A, B, C, and D down here. So we've got the number 602. So the 6 and 2 are both non-zero digits, so they're both significant. And according to rule number 4, a zero in between counts as a significant digit. So this one has 3 sig figs. Number B, 1.10. How many sig figs do you think that is? So according to rule number 3, all zeros at the end of a number that has a decimal point is significant. So this has a decimal point, and 1 and 1 are non-zero numbers. So this one has 3 significant figures. So do you know the answers to C and D? So pause and answer them all. Are you ready? So they all 4 of them have 3 significant figures. So number C is because of number 5, there's no decimal point. So there's no reason for us to think that they're not estimating. So that one does not count as a significant figure. And then this one we skip until we find the first non-zero digit. So 907. So we have 3 significant figures. All right. Now, dimensional analysis is calculating using significant figures. So let's suppose that we're supposed to find the volume of this block of wood. So length times width times height. We've got the length is 4.4 and 55 hundredths centimeters. The width is 9 and 10 hundredths centimeters, and the height is 2.54 centimeters. So if we multiply all 4 of these all 3 of these numbers, we get 105.1687 centimeters cubed, or cubic centimeters. So, we've got 3 significant figures here, 3 significant figures here, 3 significant figures here, and we have 7 significant figures here. Does that seem right to you? That we're multiplying 3 things with 3 significant figures and then expect that our answer should have 7 significant figures? That sounds a little questionable. So the answer is no, and we need to only count the first 3 significant figures. So our answer should be 105 cubic centimeters. So if you probably guessed right then that I'm probably getting ready to show you some rules about how to do math problems with significant figures, you're correct. So we're going to talk about the rules for when you add and subtract and the rules for when you multiply and divide. So for addition and subtraction, the rule is to round your number to the place which has the first uncertainty. So this is a little awkward to word because your book, I think, said the greatest uncertainty I'm not sure, but I think if I explain it, it'll make sense, but I just don't know exactly what word to use. So here we've got three numbers that we are adding together. And that the 9 right here was supposed to be yellow. So the uncertain number here is the 1. The uncertain number here is the 0. And the uncertain here is the 9. And of course, we have to keep all the places straight when we're adding. So we bring down the 9, we bring down the 1, we bring down the 6, the 7 plus 3 is 10, carry the 1. We have 81.0619. So when we scan to the right, the first digit that we've got an uncertain number in is our second number that we added, 65.30. So this 0 is in the hundredths place, and that needs to be the number, the digit that we stop with. That's our first uncertain number, and we can only have one uncertain digit in with our significant figures. So we need to stop at the 6. So I drew that red line there. Now we need to look at the number to the right of the 6 and decide if it's 5 or greater, then we would round up and make that 6 into a 7. But if it's not, if it's 4 or less, then we leave it alone. So our final answer is going to be right here, 81.06 grams. All right, so that's our first problem. Oh, well, okay, this number right here was the one that had the first digit that was going to be uncertain. So it got chosen as the winner chicken dinner. Now, this problem down here is a subtraction problem. And when we subtract 5 minus 5, 2 minus 2, we have 0. 0 minus 3 is 7. When we borrow and make that a 10. So you might be tempted just to leave this as 7 milliliters, but if someone went to the trouble to measure this out, they have 2 decimal places. And just because the answer is 0, don't throw those 2 decimal places away. So they both have the hundredths place for the decimal, and that counts. And so our answer needs to have a hundredths place after the decimal for our answer. So zeros can be significant. They're important, even though they're zeros, but they are a number and they count for, they're important to note. All right, now the rule for multiplication and division. Round your answer to the same number of significant figures as whichever factor has the smallest number of significant figures. Now, again, that's kind of hard to understand all those words, but let me show you what I mean. So here we've got 2 numbers that we're going to multiply and 1 number we're going to divide. And this one over here has 3 significant figures. This one right here only has the 1. So we have to scan until we find the non-zero digit. That's the only one. So it's 1 significant figure. Then this one has 5 significant figures. So this one is the one with the smallest number of significant figures. So it determines how many significant figures our answer can have. So we're stuck with only 1 significant figure. Now, this is our answer. So we have to throw away some numbers, discard them. and we can only keep one significant number. So our final answer, we can only keep this one. We look to the right and that number is less than 5, so we do not round up. So our final answer is 0.001, which is 1/1000th. Or we could do scientific notation and say 1 times 10 to the negative third. All right, so now we're going to talk about problem solving strategies. This is on page 16 of your book. And this is to do dimensional analysis or calculations using significant figures. So number one, we have to study and understand the problem. We need to read over it and just make sure that we understand what we're trying to do. Number two, this is a great idea. First of all, jot down the units that you're given and then leave a space and then write on the other side of the page the new units that the problem is asking for. And then number three, in that space that you have between, write down, just brainstorm any kind of connections or things that you can think of that would bridge the gap to converting the thing on the left into the thing on the right. So it doesn't matter if you don't use them, but just go ahead and brainstorm the things that you think you might need. Then number four, solve your problem. So arrange all the conversion factors in the middle that you think would help you, and see if you can cross out all the units and come up with only the units that you need on the right. When you finally, number five, after you've finished and you're satisfied, look over the problem one more time and make sure that you think your answer that you got makes sense and that you that it looks like you solved it right. So I mentioned conversion factors, and you may not know what that is, but a conversion factor is a relationship that is known between two units that express the same property. They are equal to each other. It's like when you have one over the top of the other one, they are equal to 1. So an example is 100 centimeters over 1 meter. Or you can flip-flop it and have 1 meter over 100 centimeters because they're equal to each other. Now, 365 days is in 1 year. So you could have that on the top and the 1 year on the bottom, or you could have 1 year on the top and 365 days on the bottom. And I know that we have a quarter of a day every 4 years. So we can, whenever that's important, we can figure that out. But for our problems, we're just going to count that there's 365 days in a year. There's 60 weeks. There's 60 minutes in an hour. I mistyped that. Or there's 1 hour is equal to 60 minutes, not 60 seconds. I messed up there. So how many minutes? Our question is, how many minutes are in exactly 2 weeks? So this is going to be like a boxing match. We're going to have our first fighter over here on the left and our other one over here on the right. And we're going to brainstorm in the middle anything that we think of that connect, any facts that we know that connects weeks to minutes. So first of all, we know a week is 7 days. We know a day is 24 hours, and we know an hour is 60 minutes. So we could have 1 week over 7 days, or 7 days over a week, 1 day over 24 hours, or 24 hours over 1 day, or 1 hour over 60 minutes, or 60 minutes over 1 hour. Okay, so then, now I think this part's kind of fun, but it's going to take a little practice. So don't get impatient with yourself right away. So we're going to string out these conversion factors until they're like a trail of dominoes. And then we can just crisscross, crisscross until they're all gone except for the unit that we're looking for on the right. So let me show you what I mean. Okay, so we've got 2 weeks. Now, since we have weeks up here and we do not have weeks over here, we have to get rid of the weeks. So I put week on the bottom, and 1 week is equal to 7 days. So I put that on the top. Okay, now we have days here and we need to get rid of days. So I put day on the bottom. 1 day is equal to 24 hours. Okay, now we've got to get rid of hours. So I put hours over here. 1 hour is equal to 60 minutes, and minutes is what we want, so we can stop. Okay, now watch how fun it is to cross it all out. So we can cross out weeks and week. It doesn't matter if there's an S on one or not an S on the other, if they're the same thing. Then we're going to cross out the days. Then we're going to cross out the hours. And now all that we have left is minutes. So you can use your calculator and multiply 2 times 7 times 24 times 60, and it's that many minutes. So 20,160 minutes is our answer. All right. Now, normally, or a lot of problems, we have to figure out how many significant figures that we have. But in this particular problem, they ask how many minutes are in exactly 2 weeks. So 2 weeks is a definable amount of time. We used days, hours, and minutes, and those are all defined times. Nothing was estimated. There's no uncertain digit at all. So we don't have to get rid of any digits or round or anything. So we can keep all of these numbers. Our final answer is 20,160 minutes. Now, question 2, we're going to convert 960 minutes to hours. So I've already written 960 minutes on the left and a question mark hours on the right. So we know how many minutes are in an hour. So 60 minutes are in an hour, or 1 hour is 60 minutes. So we could use either one of those. But we have minutes here, so we need to put something with minutes on the bottom. And this one has minutes on the bottom. So we're going to multiply this by 1 hour over 60 minutes. And then we need to cross out the minutes, and our answer is in hours. So we can multiply 960 times 1 and divide that by 60, and we get 16 hours. All right. Now our next question is convert, let's see, this is 100 thousandths. So 590 100 thousandths of a gram, to convert that to milligrams. So I've already written the number 0.00590 grams on the left and question mark milligrams on the right. So do we know how many milligrams are in a, how many milligrams are in a gram? So it's similar to millimeters in a meter. You know, there's 1,000 milliliters or milligrams in a gram. So 1,000 milligrams per gram, or 1 gram times 1,000 milligrams. Now we have grams over here, so we want grams to be in the denominator. So that means we need to multiply by this one. All right. So when we multiply by 1,000, that means we can move our decimal over 3 places. So our answer will be 5.90 milligrams. All right. Now let's stop and look back and check our significant figures. So here we're multiplying. So multiplying, we look at our, if they are not defined exact numbers, then we look at whichever number has the least number of significant figures. We've got 960 minutes. So this 0, since there's not a decimal after it, it only counts as 2 significant figures. Okay, the rest are definitions. So, and our answer only has 2 significant figures. So we're okay here. We don't have to make any changes. Now this one, how many significant figures does this number have? It has 3, right? And this one, these are they're defined amounts. So we don't have to count their significant figures. Only this one. So we have 3 significant figures, and our answer has 3 significant figures. So we don't have to change anything on that one either. So we are good and ready for question number 4. So here's a hungry little squirrel. Suppose he were to eat 25 grams of food every day for a year. How many kilograms of food would that be? So we've got 25 grams on the left. We've got kilograms on the right. Now this one's a little bit trickier because we've got this every day for a year amount in the middle. So we need to brainstorm some things about grams to kilograms and days in a year. So we know there are 365 days in a year. 1 year is 365 days. We can flip-flop that whichever one. And then there are 1,000 grams in 1 kilogram, or 1 kilogram has 1,000 grams. So we've got grams, and we need to get rid of the grams. So this one has grams in the denominator. And then this is 25 grams in a day, and we're needing it to go to a year. So 25 grams in a day, and we need the grams to cancel out. So that's going to change it to kilograms in a day, and then we'll need the day to cancel out. And there's 365 days in a year. So let's cancel all the things out that we can and see what we have left. So the grams and the days, and then we've got kilograms and a year left. So we need to find out how many kilograms the squirrel's going to eat in a year's time. So how many kilograms per year? So that's what we want for our answer. All right, so that's going to be 9.125 kilograms per year. So he would eat 9.125 kilograms. Now, don't forget to adjust for the significant figures. Which numbers were not exact measures or definitions? So this is a definition, that's a definition. The 25 grams is the only number that we had that was not a definition. So it has 2 significant figures. Therefore, our answer can only have 2 significant figures. So we're going to have to stop after the 1. So we look at this next number and it is less than 5. So we do not round up. So we can only say that this squirrel is going to probably eat 9.1 kilograms in a year's time. if he eats 25 grams every day for a year. All right. Number 5, convert. Now, these are just questions that some of them came from your book and some came from a different book and some were just kind of made up. So, our question number 5, convert 5.0 centimeters per second to kilometers per hour. So we've got our 5.0 centimeters per second on the left, and we need to figure out how many kilometers per hour we need. So if we brainstorm everything that we know about centimeters and kilometers and seconds and hours, then we know there are 100 centimeters in a meter, or 1 meter is 100 centimeters. At 1,000 meters are in a kilometer, or 1 kilometer is 1,000 meters. There's 60 seconds in a minute, or 1 minute is 60 seconds. 60 minutes are in an hour, or 1 hour is 60 minutes. All right. So we start out with the centimeters per second, and we need to get rid of the centimeters. So 1 meter is 60 centimeters. And now we have the meter we need to get rid of. So 1,000 meters. So 1 kilometer is 1,000 meters. We want to keep the kilometers. Okay. Now we need to get rid of the seconds and change that to an hour. So we look for something that has seconds. So we have 60 seconds is a minute. And then we need to get rid of the minute because we want an hour. So we put the minute up here. 60 minutes are in an hour. And we want the hour, so we stop here. All right. So if we multiply, well, let's cancel out our units and make sure. Cross out the centimeters, cross out the meters, cross out the seconds, cross out the minutes, and we're left with kilometers per hour. And if we multiply 5 times 1 times 1 times 60 times 60 and divide by 100 and then divide by 1,000, we get 1/1800ths of a kilometer per hour. So now don't forget to look back at our significant figures. So we were multiplying and dividing. So we look at the number with the least amount of significant figures, and we only have one number because all the rest are definitions. Conversion factors are definitions. So this one has 2 digits, and our answer has 2 digits. So we're good. We don't have to adjust anything. Thank you. And that's all. That concludes section 1.2. And I'll try to have section 1.3 maybe this week, I'm hoping, but we'll see. Thank you. See you Friday. Bye.